So I showed you something very weird in the video before. I showed you that if you take neutralized particle and expose the object, for example, an apple, so makes sense, all the particles would color this side of the apple, right? And this side would stay empty and clean. Makes sense, okay? But when we add charge, we so far talked about what happened. We add charge, now our nebulizer exposed particle with some multiplication of the electrons unit, and we talked about the particle-particle interaction, which repel each other. But what's happened to particle interact with the apple? So these particles just gonna color the apple, no question about it, but suddenly we saw something very, very weird. The particles attract into the apple and also color this side, okay? And that's what we're going to talk today, okay? Today we're going to talk about the particle-tissue interaction. Let's go into the lungs, okay? So if we see the airway of the lungs, okay, and I do zoom in into the airway, I see interaction between the particle and the tissue. So let's talk about that. So I'm going to go back to the video. So what's going to happen? So in general, we have the lungs, and the lungs have many scales, but the particle, the charged particle, would interact with the tissue. And the tissue is a very conductive, okay? And what does it mean it's conductive? It lets charges to do what they want. I would not stop you. You want to go there? No problem. You want to go there? You want to have a current? Do whatever you want. This is the idea of a conductor. And when the charged particle come close to the tissue, what we suddenly see, he starts to polarize the tissue. He starts to attract different charges next to him. And for that we have an attraction, and it's important to remember that the electrostatic force, the basic of electrostatic force, is depending on the distance squared. So we already have some intuition what would happen. So my question to you is, we have some charged particles with some electron. I know, there are 7, okay, something like that. And it's an altitude h above the tissue, okay? Do you know what? Explain to me why it's not trivial to calculate the electrostatic force. Let's go to the board. Okay. Why it's not trivial to calculate the electrostatic force? The electrostatic force, remind me what it's equal to. We know there's some electrostatic force. It's equal to what? To the charge multiplied by the electric field. Agree? The particle feels some electric field, okay? And what generates this electric field? The charges on the tissue, right? If this is positive, let's say. So it's because of some small dq on the tissue, which arrange in some function, let's call it sigma e, how much the particle dense. But we don't know that. We don't know that. We don't know that. We don't know that. And we don't know that. So we kind of screwed, right? We cannot tell what is this force equal to. But we do know some stuff. First of all, okay, we know that the tissue is a conductor, okay? And what is the meaning the tissue is a conductor? It's mean that we can say that it's grounded, it's a big conductor, right, with infinite amount of charges, right? So, and we also can say that the potential here is 0 of the conductor, right? And we also can say that the electric field in the conductor is 0. Why the electric field in the conductor is 0? I have a cool demonstration from physics 2 if you don't remember. So let's do that and that and that. You know what? We can do it on that. Okay? So where's my phone? This is my phone. Okay. Can you call me? So if somebody is calling me, okay, there's electric field. Go to the satellite and go back to my phone, and then my phone gonna ring. Okay? I'm gonna prepare for the demonstration. Here, you hear it? Okay, don't call me. Hang up. And now what I'm gonna do, I'm gonna take a conductor, right? This is a conductor, and I'm gonna wrap up my phone with the conductor. Okay? This is my phone. I'm 100%, you can call me, okay? You can call me. And what conductors do? Conductor let charge do whatever they want. And if some electric field coming from space, the charge rearrange themselves to obey this electric field and actually cancel it inside. You call me? Put speaker. There's no way. Okay, I'm unavailable. This is what happened to you when you go into the elevator. Okay? And this happened because this is a conductor. You see? Wood is not a conductor. Right? You see in the camera? Wood is not a conductor. Aluminum is a conductor. And I have here, not for the soft hard in the audience, I have here a mouth of a pig, okay, which is the beginning of the reciprocatory system, okay? So I can put this here. The lung is a conductive, okay? So the electric field within the tissue, it's disgusting, guys. Okay, if you want to see it, okay, so I put it here, and I see it's a conductive. It's closed the circuit. Okay, so I know I can treat the tissue as a conductive, and there's two interesting things about the conductors. Okay, first of all, where is my? Here it is. Okay, so first of all, I know the electric field is 0, but I know another thing. Another thing, I don't know if you remember, is that the electric field is 90 degrees to the conductor, okay? Which means the electric field to the conductor is at the minus z direction if this is z, okay? This is a very important phenomenon. The electric field direction is in that matter. And now let's go to the board. So I remind you, we screwed up. We don't know what to do, but I have some solution, okay? It's not perfect, but some solution. I'm going to do a quick reminder on physics 2, electromagnetisms, but you don't need to know everything, okay? I'm just going to tell you what is really important. I want you to have the intuition, okay? So we learn in physics 2, Gauss's law, which tells how electric field behave, and also the definition of potential, voltage, energy kind of thing, right? Because this is what we know about the conductor. Okay, we know the potential is 0, the human body is huge, infinite amount of charges, and we know the charge distribution, produce electric field, follow Gauss's law. You can be more elegant and present the same equation as a derivative and vectors, right? Not something new, nabla and all this stuff. Okay, you can combine the two equations and have a very interesting equation, okay, which is Poisson equation. So this is the most important equation when you talk about electrostatic. And what's really important about this equation is this thing. This thing is said, derived by space twice. If I want to find a solution to that problem, how many boundary conditions do I need? 2, okay? One of the potential and one of the gradient of the potential, right? The derivative. And the gradient of the potential, it's the definition of electric field, right? So you need 2 boundary conditions, okay? So what I'm going to do, okay? I'm going to go to the board. I don't know how to solve it, okay? I don't know how to solve it, but I'm going to teach you a trick, okay? A trick which called the uniqueness theory, okay? Theorem. The uniqueness, it's called the uniqueness theorem. And what these things say, it say, maybe you don't know how to solve your problem. But if you have some volume in space, okay, some volume, I got some volume in space, this one, okay? I got this volume above the airway, right, above the tissue, inside the airway. So if you got the volume, and you know your charges, there can be many charges, but you know where are the charges, okay? Volume with Q's, okay? Many charges, and you want to find the solution for voltage or for electric field. Doesn't matter, they are the same. Yes, I want to find electric field because then I will know the force. That's exactly what we want. If you want to know, you just need to verify that the boundary conditions, the 2 boundary conditions of voltage and the derivative of the voltage, yeah, let's do phi, not to confuse the volume, which is actually the electric field, are the same in the boundary conditions. If you want, I did not tell you what, but if you have a volume with known charge, and you obey the boundary conditions, the two boundary conditions around this volume, the solution to your problem for Poisson equation is the same. Which means I don't need to solve that thing. I can solve much easier problem and make sure the boundary conditions are the same, the charge in space are the same, and the solution of both problems would be the same. You see what I mean? Okay? So what I'm gonna show you? Okay? So let's erase the apple. Okay? So what I'm gonna do, what I'm actually saying is that the uniqueness theorem said that the solution to the Poisson equation for this volume in space is unique. There's only one solution. You give me two boundary conditions, I cannot change the solution. You gave me the boundary equation. And what I say, I'm gonna make this boundary equation, okay? And I know that the solution in this place, the solution for Poisson equation, which is voltage or electric field, would be the same. So I don't want to solve this one. I want to solve an easier one, okay? So let's go here. So I would say something very weird, okay? Not that weird. You can have some intuition. I say that, let's think about it. If I have a positive charge next to the tissue, who would come together around here, positive or negative? Negative, okay? So kind of the tissue, if this is the particle, what the tissue do to us intuitively? It's mirroring us, okay? It does something to us, but in the opposite side. I'm right-handed, in the mirror I'm left-handed, right? I have positive charge, I have inside the mirror negative charge. So I would say maybe, I don't know if it's true, okay? I hope so. Maybe this problem, I go to the TV. Maybe this problem have the same boundary condition as our problem, and this is a very easy problem. I would say we have a positive or negative charge Q above the tissue, and we have the opposite one below. They both height h, and I wanted the boundary condition to know what is the electric field. And we know the electric field must be perpendicular, right? This is because it's a conductor, okay? Here we don't have a conductor, okay? Two charges in space, okay? So let's solve it. Here, this is one. This is better, okay? So this is our, this is B, okay? So A, we explain why it's hard to do it, and we explain what we're going to use, the uniqueness theorem. And right now we're going to see our first example. So we have the z direction, the radial direction. We have here, let's say positive, it doesn't matter, Q. And here below, in the same distance, H, yes, we have a negative charge. And my question to you is, what is the direction of the electric field? Okay, what is the direction of the electric field? Okay, so on in z equals 0. Okay, so how I can do it? I can use superposition principle, right? I can say, let's take this place, and this charge make this electric field, agreed? This charge over here makes this electric field, sorry, this is negative, this electric field, right? So if I'm gonna put them on the same axes, right, on the z and r coordinate, I'm gonna see that this one cancel because they have the same magnitude, but this one sum up. And this is a general location, right? You can think about the distance r, and this one is height h, right? So this is d, this distance. So we see that the electric field at z equals 0 is exactly what we want, right? Exactly the same direction that we want, okay? But this is not enough, okay? This is not enough. This is obey that thing, right? Equal, this one equal to, sorry. So this is perpendicular. E perpendicular to the conductor. Perfect, okay. But we need another thing. We need to know what is the potential, okay? Not only the direction, which we found. We have our first boundary condition. It doesn't mean that this problem is similar to that problem yet, because I have freedom. I have another boundary condition about the potential, okay? So let's find out the potential. So this is going to be section B. So the eraser is, where's the eraser? Oh, yes, it is. Here. So section B would be find the potential on z equals 0. Okay? The potential. So B, we want to know what is the potential at z equals 0. And just remind you, in general, potential is looking like this, different in potential, equal to R infinity E dot dr, right? This in infinity is equal to 0. So the potential at any location, but let's go with z equals 0 at any r, equal to the integral of E, some magnitude. I don't know what the magnitude, it can be a function, but it's at the what direction? Z direction. And dot dr, but we only at the z plane, right? Only at the z plane. So this is dr r, right? This one, these steps. If I want to take step here, right? And they're always perpendicular to the field, right? We have your dot, right? So this is by definition equal to 0. So the potential at z equals 0 equals 0. Aha. We satisfy the boundary condition. Let's summarize everything and make it clear, okay? So the real problem that we face is we have some charge next to a tissue, okay? And this thing make, I don't know, some probability function of charges. You see how they behave? But I have here another problem, right? Another problem, but the boundary condition of this space is the same. The field orientation is in that direction for the particle. You see, 90 degrees. Also here, the field is like this. And from here, it's like this, right? It's going that way, you see? So at this line, the electric field direction is the same. The potential here, because it's the whole human body, is voltage 0. And we found out that the potential here is also 0. This means that according to the uniqueness theory, these two solutions would be the same only for that space. You see? For that, not here. But for this place, it would be the same. We have the same Q, and the same boundary conditions. Okay? So the equation would be solved the same, just for intuition. Okay? Got it? So if I want to find what is the electric field here, next to the tissue, okay, that's going to be our next section. Go to the board. Okay? So if we found the voltage, so if I want to find the electric field in the real volume we are interested in, okay, let's go with height z equals 0. Okay, this one. We can find it. A question?
How do we know that the membrane of cells is charged?
Oh, great question. So the membrane of the cells, usually you learn that have some millivolts, right? Compared to what? Voltage is always about the difference with the fluid between the cells. Where are the particles? In the air. You see what I mean? Good question. Okay, so right now, I want to find, for example, what is the electric field above the tissue. With the original question, here, we cannot do it. But here, We can do it, right? So let's go here. So see, what is the electric field at the z height? Yeah, now we're going to find the magnitude. So, you know, using the superposition principle, yeah, we can find it very easily. Yes, we're going to say it's a contribution of two charges, right? We have the red one and the blue one. The red is the positive, right? It's k, q, divided by r squared plus d squared, h squared, h squared, right? This is the distance, just did the Pythagoras to find this distance. And the direction is r minus hz divided by the magnitude r squared plus d squared. So this is the contribution of the red one, the positive. And if we want the negative, what we need to do, sum it up. K minus q, the same distance, right? Yeah? R, but the difference is here. Now we need to go plus h. You see this one, plus a minus, minus, plus. You see it? Squared. This is just the math, you know, it's very easy. And this is equal to the total electric field in any point at this height is equal to k, q, r squared, sorry, not dh, r squared plus h squared, 1.5, 2d. Okay, 2d at the minus z direction. Yes? So this is the electric field a little bit above the tissue, above the cells. Okay? Now, let's go to the board, to the TV. So now I know the electric field, I can do something very cool. It should be H, not D. Sorry, this is H. This one is H. Okay? Okay, perfect. So right now, what I'm going to do, I can calculate how the charge behave on the tissue. Because I know the electric field above the tissue, and inside the tissue, the electric field equal to what? 0. It's a reminder. It's a conductor. Okay? So how are we going to do it? Look at here. Yeah. I'm going to come back to here in a second. All the D is H. Okay? I'm going to come back to there in a second. Thank you. So what I'm going to do, I'm going to use Gauss's law. I'm going to do this envelope. So just a reminder, what is Gauss's law? Let's go to the board and do it together. Just to note here, I wrote D. It's supposed to be H. Where else? Here. It's H. Okay? H, which is the distance between them. Perfect. So right now, we know, just a reminder, now we know the electric, let's go here. We know the electric field here. E, Z equal to 0, right? At this limit. We know it, okay? And what I'm going to do, I want to know what is this one, this function. How charge distributed around the particle. You see? It's accumulate around the particle. I want to know that. And I can use Gauss's law. Just a quick reminder. Gauss's law said, do a closed integral on some imaginary volume anyway, anyone that you want. And this must be equal to all the charge you find inside, divided by epsilon. So I'm going to take, back to here, I'm going to take this crazy shape. Okay? I'm going to take just a cylinder. We know that inside the tissue, the electric field equal to 0. And we have some charge where? In this place, which we don't know its value, right? It also can be here. Some charge distribution, which we don't know. We could call it sigma E, right? Charge per meter squared. Go back to here. So if I'm going to take my cylinder and I'm going to break it down, I can have the top, right? I can have the top of the cylinder, which has the area pi r squared, multiplied by the electric field there. If I do it very small cylinder, so this is K, Q minus 2Z, right? 2Z r squared plus Z squared 1.5, right, plus, okay? Now I can have the rest of the envelope, right? What is the rest of the envelope? The rest of the envelope, we have this thing, right? This side, but the electric field in this direction and the dA in this direction, right? So the sides, dA perpendicular to E, so this is 0, plus inside E equal to 0, right? Because it's a tissue. What is the charge that we have? We have some charge density, which we don't know, multiplied by the area of our cylinder, okay? This is canceling out, right? And we're gonna get sigma E equal to minus Q Z 2 pi. Z, sorry, I put Z, but it's H, okay? So what, let me clean it. So what I did, Z is the height of the particle, okay? So what I want to show you, the height of the particle, okay, is changing. You see here, it was H. So if it's dynamic, which means the particle getting closer and closer, what's happened to the charge? Accumulate around the particle, right? So minus QZ 2 pi R square plus Z square 1.5. So this is the charge density, Coulomb per meter. And if you're going to draw it, it's going to look like some Gaussian. Similar. It's not a Gaussian, but it's similar. A lot of particle would accumulate here. You see? Okay? And if I'm going to do an integral, what is the total charge on the tissue? The total amount of charge. I can do sigma E dr r d theta, right? This is dA, right? And I can run from 0 to 2 pi on theta, and from 0 to infinity in the distance. And you're going to get, this is equal to minus Q. So all the charge that we have on the tissue is minus Q. And there's no surprise, because we found that this solution makes sense. Okay? Good. Again? Okay, the bottom, that's a good question. So this is the upper part. So the upper part, you have an electric field, the height of the particle, right? And the side's equal to 0 because of that. But inside the tissue, the bottom is absolutely 0. Why? You cannot use that, right? Because this is not valid. Our solution valid only to this volume, right? Not to this one. So what I did, I look at the equation, at my problem, and I say, haha, this is the tissue. And this is what? Conductive. Right? In a conductive, we say the electric field is always 0. And that's the reason my phone right now doesn't have any reception. Okay? Let's try to be quick, okay? Let's try to be quick. Aha, you see no reception? And now it's gonna correct itself. Now it's going to get a reception step by step, okay? Because the conductive envelope doesn't interfere with the electric field. Very good. Okay. So this is the charge distribution on the tissue below the particle. And I'm going to give you something cool to do with the charge distribution at the homework. Good. But now, guys, we got to the most important question. What is the force on the particle, right? That's why we are here. Agreed? So let's go here to this side. So now the question is, what is the let's go to the board, to the TV. So right now we found out the charge density. We know the we can calculate the electric field, right? We can do whatever we want. And why we are doing that? We want to understand what is the dynamic of the particle, to know what the force apply on the particle and compare them to the other forces. So just to give you a taste what you're going to do at the final project, I want to show you that, for example, in this model, you know it very well. So in this project, we have two sides of model. One is sick, okay, with constricted disease, asthma or COPD, something bad, and the diameter shrink and the velocity reduce, and the other side is healthy. And here you can see what you did in the last homework, the particle trajectory. But now we also have electrostatic effect. And what we see, for example, that if particles started here, when you go to the split, we run two different simulations, the normal side and the constricted size. And we see that because of electrostatic, the particle deposit in the sick place versus the one in the normal, which exit the model. You see, it almost did not deposit. This is a half micron, 200 electrons. You see? So that is very interesting, and that's what we actually want to do, to compare the electrostatic force. So that's the question that we have right now, the most important question. What is the electrostatic force on the particle? Okay, going back to here. Okay, so there's two ways to do it, to find the electrostatic force. One is to say, aha, I know the charge density, right? I can divide the tissue to small dq, each one produce electric field, right? To see how it affects the particle, small force, and sum up all the forces of all the small particles. Yes, you can do that. That's a good idea. However, you can say, wait, the force exists in this volume, right? This is the force, right? This is the force. I know it. It's here, right? I can use the uniqueness theorem to find the force. I can use this thing and not this thing. We found this for nothing, okay? It's just going to give us understanding what's happened to all the ions on the tissue. They're doing that, okay? But in order to find the force, I just need that. I can say here, let's make it similar to your homework, your simulation, right? So we have some charge. Let's do a clean one. So it's going to be organized for you. So we have this thing. We have y-axis and an x-axis. And we have particle in the height, general y. Agreed? In order to solve that, we're going to use the uniqueness theorem, because we know this problem with the particle at the distance y here and y here, with the same charge, this q, this is minus q, going to give us the same electric field, right, in space. So the force of the particle-tissue interaction, it's k, right? Q squared, because they have the same sign, right? The distance between them is 2y squared, agreed? And the direction is minus y. It's always an attraction. If this was negative, here I should put positive, right? So it's always an attractive force, okay? So this is the particle-tissue. This is not the one. Here it is. Very good. Particle, tissue. And something that I want to say, which is very important, charges, particles, almost always charged. To find particle with no charge is very rare, very, okay? Even this cube of air have a lot of particles, some of them positive, some of them negative, they cancel out, it's neutralized. But the individual particle is charged. So this force was always there. Even if you neglect it, it's always here, okay? And what's happened? If there's a particle and you do a free fall, okay? Gravity, very heavy. But when it's going to be really close to the tissue, this is going to be huge. There's some distance when this force is going to overcome gravity. You understand, right? There's some distance that this particle would overcome Stokes, diffusion. So electrostatic always win. Always. The question is, from what distance? Okay? But every time this effect was in the human body. Agreed? Understand? So after we found this particle-tissue interaction, we want to take care when does it count. Okay? So going back to our original discussion, we did it for space charge in the previous class. So right now we're going to update this, not to the space, but to electrostatic. Here's the blue for electrostatic. And let's see what's happened. So the electrostatic force is K, right? K, Q squared divided by 4y squared, right? 2 squared, so it's 4, and minus y direction. That's true. And when I do the non-dimensional analysis, okay, so we have something to deal with the velocity, we have something to deal with gravity, we have something to deal with time, but right now we need to talk about y. See? Because we need to non-dimensional also this one, right? By the way, we non-dimensional q. Just a reminder, q equal to ne, right? We kind of non-dimensional it, yes? Ne, okay, so n, it's like the non-dimensional of charge, q divided by e, right? So we need to talk about y. So what is an appropriate length scale to see that electrostatic is working? What we should put here? Not an easy question. The first guess would be the diameter. It's a length scale, right? But if I put here d, the distance from here to here is crazy. You see, it's so small. So, smaller, it must be smaller than diameter. Agreed, okay? So maybe the radius, okay? But in the radius, we have symmetry. So the attraction from here and the attraction from here cancel out. So it must be smaller than the radius to make sense. So this force would be significant. Remember, it's a particle-tissue interaction. Okay? So the most appropriate way to say it, some correction from the radius. We can give it to be x, okay? Capital X, some number. In most of the literature, this value is 0.05, okay? 5% height. If all the particle from the 5% height gonna account, if you do the math for a cylinder, it's gonna be 10% of the total volume, okay? So 10% of the total volume is significant, okay? Remember, only the particle in the edges are the ones that are gonna deposit, right? From gravity, from diffusion, maybe not from stock, okay? But for most particles, okay? So this is the one that's most common, but I give you the freedom to choose whatever you like because I don't like this, okay? So, okay, it's cool? Good. So if you're going to do this thing, 5%, we're going to get a non-dimensional equation, okay? We can do it here, R or Y, yeah, it's the same, okay? So here we're going to get H, gravity become the H number, plus effect of electrostatic. So this effect is called INC, from the word induced charge. Because what's happened? The particle come close to the tissue, and what it did to the tissue? It's induced charge on it. There's no new charge. It was here all the time. It just separated to charge close to the tissue and charge far away from the tissue. Repulsion and attraction, right? So it's called induced charge, and the magnitude of it, it's very similar to the space charge. Okay, don't get me wrong. It looks here. It's here. It looks like this. It looks like Ke, Coulomb constant, the mechanical mobility divided by the velocity multiplied by Ne versus 2xd squared. Sorry, I put here. Okay, you can put R, you can put D. Okay? Yeah, okay. There's a freedom with X, okay? So it really depends what the people are asking for you. So I wrote 2x, so let's write here D. Okay, it's just multiply this by 2. Okay, it doesn't that matter. Okay? Good? Nice. So we have that. This is URL. Okay, URL is non-dimensional number which equal to 1, which means if this one is much bigger than 1, most of the particle would deposit by gravity. If this number much bigger than 1, most of the particle would deposit by electrostatic. If stock number, which is this, much larger than 1, most particle would deposit by stock. And if one of them is bigger than the other, you can also neglect this mechanism. That's the idea. And we did not put here diffusion because it's a little bit complicated. We do only non-dimensional for that equation. Yeah, okay. So we said that it's not true to put the diameter as the length scale. It's not working, right? It's not a good way to do it, right? So what we should put here instead of the diameter, so the way to answer it, put whatever you want. We're going to call it x, okay? And in the literature, x is 0.5. Some people more cautious and put 0.025, actually less cautious, okay? So it's some distance you want to compare from the diameter, but what I want to say is this must be at least 1/10 of the diameter, right? Quarter of the diameter. It could not be radius, it could not be the diameter. It doesn't make sense because the ink effect is not happening that far from the tissue. You see what I mean? Perfect. Okay, so we talked about that. This is the non-dimensionals, and right now, to the last section of the tutorial, let's find out what is the ratio between these non-dimensionals, okay? The particle-thinker interaction versus all of this. And luckily, we still have this, right? So we can just cancel space, space, space from the last hour, space. And we can talk about right now to put ink instead of space. So if we're going to put ink versus H, what we're going to get? So it's Ke, right? B, the mobility, divided by U, multiply by the charge, and E squared divided by the distance, right? That's what we have. We see that U cancel. What this means? That U cancel. That the pattern of flow, breathing, right? Doesn't matter. Why? It makes sense. If the particle wants to deposit, think about it. If you have a velocity, you want to have as much as velocity to have time to deposit, right? Because the image charge would become closer, the force would be stronger. You want to have the smaller velocity you can. The same thing with what? Gravity. Gravity also wants a lot of time to deposit. So that makes completely sense. We again see B and tau. You see them? So this is 1/m, which means small particle prone to electrostatic versus big particles. Makes sense, right? Good. So this and this become this. We have down below mg, and above, no surprise as before, we see that we have the electrostatic force. So this is just a comparison between the two forces. Makes sense. What happened with stock? Ink versus stock. Ke/B over U, Ne 2xd to the square. We see that U is not canceling, which means we have the velocity very, very taking care of the ratio between them. We see again that B and tau become M, and we see kind of a kinetic energy. You have a lot of kinetic energy, stock would win. You don't have a lot of kinetic energy, ink would win. Okay, the induced charge effect. Perfect. D go upstairs. This is D, right? And here we have Ke Ne square 2xd. Actually, we can take this D out, right? Because you have D squared here, and put here D, right? This is the effect. So that's what we have. As deeper as you go, electrostatic become more significant than stock. Because as deeper as you go, D decrease and velocity decrease, and it's squared, right? You see it? And again, related to the ratio that you have, okay? If you remember, we said that Cp, right? Cp is reducing in the lungs because the particle deposit and the volume increase, right? Volume to the third. What's happened to electrostatics? This mechanism. This is the individual particles. So they lose charge, they gain charge. So the answer to that, if you use powders to inhalation, they're not going to lose charge. almost at all, because they have a great resistance. They will not let the charge to move. Like the conductor give charges the freedom to move, resistors don't let them move, okay? So powders usually have a lot of resistance and charge will not change. Example, dry powder inhaler. For droplets, that could be changed. So for droplets, maybe charge can run away. So if I'm a droplet and I'm conductive and a water droplet hit me, it can gain some of my charge. So it can reduce. However, the time spent in the lungs is merely 1 second. I don't know if you did your simulation already, but you see it's very fast. It's 1.5, 2.5 seconds, go to the end and back, right? So it doesn't have a lot of time to lose charge, okay? Versus the concentration, which die very quickly. And also, you cannot give a lot of concentration. Why? You cannot do it. Why you cannot give a lot of concentration of medicine? Exactly, there's a limit, because the people would start to it's too much, right? You cannot play with that too much. Great. So you found that one, perfect. And now, what we see here, what drives us is to say, small particles are the best candidate to enjoy electrostatic. However, small particles also the best candidate to enjoy diffusion. And for that, this ratio is also interesting. So if you're going to do this, we're going to see something very interesting again, that U and U cancel. Again, velocity doesn't play a role. I have more time to diffuse. This has happened because U related to the normalization of time. Remember? We did that the average time you spend is the distance versus the velocity. This is the reason it's here. Good. We see B, but we know that diffusion also consists of mechanical mobility. So we again see that the shape of the particles, okay, the size of the particles, the fluid, you can have helium and you can have air. It doesn't matter. Hot air, cold air. Actually, temperature do matter because you have here T. Yeah? But the flow doesn't matter, the material itself. Okay? B cancel. D. Okay. So here we have this one. We have KE. Ne2x d squared, right? And this multiplied by d. But remember that here you have 2d, right? You have d squared. So this one actually become 1 over d. So we see a big major with space charge. Space charge, we have d, now it's 1 over. This means that the induced charge effect enjoy the small spaces more than diffusion. So most of the people say, in the alveoli, diffusion is the most important mechanism. Not if you have a lot of charge. Charge would be much more significant. Yes? And we also can compare a new non-dimensional number. We can also do, help me with this one because I don't have it in my notes. We can compare ink versus space. That's what happened to the apple, right? You can compare this. So this equal to, what is space charge? Remind me, this is K, this is B, this is U. Also here, K, B, and U cancel out. Here we have NECP to the third squared. And here, this was the space to the third, right? And here we have NE, right? 2XD. You see it? NE and NE cancel, and what we left is that CP, we have 1 over 2XD, right? Squared, CP to the third, 2/3, right? That's what we have, okay? Yes. Yeah, that's what we have. So this is the ratio between ink and space. And we know that this is becoming very small in the deep region, which make ink very, very strong. And we see that the diameter goes small, ink again win, okay? So something to think on. So you have this one, you have this one, right? You have here KBT, don't forget, KE, KE. Good. Let's go to the presentation. So just to have a little bit feeling what's going on here. So that's, for example, simulation that I did. You see it's a half micron, 15 liters per minute, normal breathing rate. Yes, 600 electron. And we see the non-dimensional numbers. We see ink, H, and stock. We see that the initial in the trachea, the upper airway, stock is very strong. You see? It's overcome all of them. And it's important to notice something that for me was really shocking at the beginning. What are the numbers here? 10 to the minus 4. That means that most of the particles in the lungs, most of the particles by the lungs, all these mechanisms smaller than 1. See, camera? What does it mean? It means that most of this non-dimensional number, URL, present the relative velocity between the particle and the flow. So if this is equal to 1, and it's much bigger than the others, it means that most of the particle we inhale in the lungs follow the flow. That's what they do, okay? You need very big diameter to be very heavy to get over 1, and that's what you see in the homework, right? You need to have a lot of electrostatic charge to overcome 1, okay? So that's what happens, okay? So that's what I wanted to show here. But you see that when velocity decreases, what happened to gravity? Waking up, you see it? So this is stock, of course, and at some point gravity is more important than stock, okay? When we go inside, I want you to see what's happened in generation 18, where the acinar coming into phase. So I put here ink. You see that electrostatic is more important than gravity for that particular case. Okay? You see what I mean? So what we did, okay, just a summary. So we take the particle dynamic, okay, and it's very hard to solve it. Very hard. By the way, you're going to solve it, okay? We're going to talk about it. But it's very hard to solve it, especially when you add the electrostatic force. Now the equation becomes non-linear, and that's going to be the topic of next time, okay? The last tutorial, which is going to be a preparation to the final project. And by non-dimensionals, we present a different mechanism that make the position. For example, heavy particle like this truck could not take the turn. So the truck deposits on the side of the road, right? Okay, this is the stock number. We have the effect of the molecules of the air pushing the particle. This is the diffusion mechanism. And if we are very heavy, also gravitational force, the H number. And right now we learn a new one, which is the induced charge or the space charge, up to you, what problem you solve, which also affected. And it's important to notice that all of them depend on the characteristic velocity and the characteristic length of the problem, which generation I am. And if we zoom into the lung is a multi-scale problem. We start with the centimeter and ending up with micrometers, okay? So the length change, the velocity change dramatically. And for that reason, when somebody been investigated electrostatic only in the upper airway, it's a joke, because it's completely changed its role in other places, okay? So just to show you, to give you a taste, I did a non-dimensional, okay, a 2D map of non-dimensional, when we have charge, many kind of charges from different inhalers, and many different sizes. And for each one, I compare who is dominant. And for the big particles, gravity, of course, obvious. And for the small particle, diffusion, makes sense. But I want you to see that for just merely 20 electrons, it's nothing 20 electrons. Charge is governed the situation in the deep region of the lungs. And this was my case for my PhD. In PhD, I showed that and said, what? Nobody investigated electrostatic in the deep region of the airways. And that's the reason I say, guys, there's a lot of opportunity in the deep region of the lungs to cure medicine, because all the diseases happening where? In the alveoli and the terminal bronchioles. This is the place of disease. This is the place where you want to do drug delivery, systemically to the blood or to the lung itself, localized treatment. Okay? So, and also, I was not the first one to notice it. I came to Jeswell lab, and Rami, one of the students that established the lab with him, Dr. Rami Fischler, he said, Ron, you must see something. After your talk, you see this Donald duck, how it's kidnapped? This is very similar to the y-squared effect in the denominator of the electrostatic. What's happened? As close in as you get, suddenly the electrostatic force is so strong, you cannot get away. And he told me, Ron, you must see video from years ago that I saw. And he showed me this video. He built the alveoli, a breathing alveoli, and I wanted to see this particle. Against gravity, what this particle did? What was the mechanism? Electrostatic. So electrostatic is very, very important. So next time we are meeting, we're going to talk a little bit about your final project. In the final project, what you're going to do, you're going to put everything together and going to solve Newton's second law. Don't worry, I'm going to guide you. Okay, guys? Any questions? See you next time.